Okay, in the last video, we introduced the equilibrium constant. And basically what the equilibrium constant was, was a value that was a function of the temperature of the products, and it was associated with a particular reaction within the products. And so what we saw last time was that equilibrium constant, which can be determined and can be tabulated as a function of temperature, can be given in a table. And that particular constant, which ranges from very large numbers to very small numbers, typically is presented as the log of the magnitude, either the log base e or the log base 10. And so we know when we have a log base 10 and the number is, let's say, -2, that this really corresponds to a equilibrium constant that is 10 to the -2 or 100th in size. And so what this then tells us, if we look at the definition of the equilibrium constant, that it's directly related to the right-hand side of the reaction equation. Those are the molecules that represent C and D divided by the left-hand side of the reaction equation, which are the molecules representing A and B. And so when we present then for a given reaction equation, we write the equation itself, and we represent what's on the left of the equation as the A and the B values, and what's on the right of the equation are the C and the D. And so this equilibrium constant represents the mole fractions of the components, the CD components. And so it's basically the magnitude of this number is telling us how quickly or how far the reaction goes in the direction to the right. And so if we have a really large value of K, it would imply that what remains are the components on the right side of the reaction equation, and what is minimized are the components on the left side. So a very large value of K, which would correspond to numbers in this table that are positive or greater than 0, it would represent then reactions that are primarily going to the right. Very small numbers, which would represent numbers that are highly negative, would say that the system is predominantly going to the left. And so for this one reaction that we looked at low temperatures, what that's saying is water primarily stays as water and does not have a tendency to dissociate into these two other components. Likewise, when we look at like diatomic oxygen and diatomic nitrogen, because of their highly negative values of equilibrium constants, they say that at given temperatures, the molecule pretty much stays as the diatomic molecule. And only when this K gets to be, gets greater than, let's say, greater than 0, do we start to see the presence of some of the things on the right-hand side showing up. And so the equilibrium constant that we saw before, which is defined in this particular fashion, can be written as instead of the mole fractions, could actually be written as the number of moles on the right-hand side, which are the C and the D, divided by the number of moles on the left, which are the A's and the B's, dividing by capital small n, which is the total number of moles. And so all that this equation is doing is writing the equilibrium composition or constant in terms of moles instead of mole fractions. The final piece of information that we obtain from the value of K is that K is a function of temperature, but as we see, there's also the mixture pressure is associated with the system. And so we see that pressure has a tendency to cause the reaction to go either to the right or to the left. And it all boils down to the summation of the stoichiometric coefficients. And so the C and the D minus the A and the B. And so what that tells us is that when we have a reaction where the A's and the B's are the same as the C's and the D's, for instance, this reaction right here, because the A and the B are 1 and 1, and the C and the D are 1 and 1, we see that this particular reaction has no effect with respect to pressure. So pressure does not come into play. But when we look at something like this, where the coefficient on the right is a 2 and the coefficient on the left is a 1, what that tells us is that the coefficients on the left minus the coefficients on the right, this then would say that reaction has a pressure to the first power. And so this pressure term will have an effect. If you double the pressure, you're going to find that this term will double, which will then cause the coefficients to change accordingly. And so when you talk about whether or not the reaction is going one way or the other, not only is there a temperature effect, but there's also a possible pressure effect. And in fact, the pressure effect could actually counteract the temperature effect. So let's look at a really simple problem. And this simple problem is such that it's asking us if we had CO and CO is combining with 1/2 O2. Well, typically, if we were to use Chapter 13, Chapter 13 says that this reaction would go to 1 CO2, okay, because the carbon and the oxygen, and then here's another oxygen, the reaction would just be these two reactants forming 1 CO2. Now, in this particular case, if Z was equal to 0, that would be 1 CO2. And because we may have some of the carbon going to CO, if we said that ZCO was formed, that would then cause the CO2 to be 1 minus Z being formed. And then because of the fact that a carbon is forming with just a single oxidizer, that means that there's going to be some oxygen left over. And so this is a balanced equation that corresponds to carbon and oxygen, but again, Z is not determined. Okay, we cannot determine Z, we cannot determine the Z by just balancing the equation. And so this would be a scenario where if one wanted to know at a given temperature and pressure how much CO2 dissociates into CO, the other piece of information that one would need to calculate the Z would be the equilibrium constant. And so this is just a hand calculation wherein one assumes that this is the products. Z is unknown, and with Z being unknown, the total number of moles on the right hand side would then be equal to 2 plus Z over 2, and that in equilibrium, each of these three components would have a corresponding mole fraction. And the mole fraction would be the number of moles divided by the total number of moles. And so for CO, it would be Z over 2 plus Z over 2. And so that would be the mole fraction of CO. This would be the mole fraction of O2, and this would be the mole fraction of CO2. And so with that information known, then we can go and we could say at a given temperature, what is the equilibrium constant? And so we could say at equilibrium, the tendency of CO and O2 to form CO2 would balance the tendency of CO2 to form CO and O2. And so this is the equation then that one would be interested in using as our second equation. CO2 going to CO and 1/2 O2. Now, that would then correspond to this equation right here. CO2 going to CO plus 1/2 O2. CO2 going to CO plus 1/2 O2. And so because we now can write the value of K being related to the mole fractions of CO times the mole fraction of O2, each of them raise to a corresponding power, a power of 1, a power of 1/2, divided by then the mole fraction of CO2 raised to its power of 1, and then dividing that by the total number of moles, we then have an expression that relates the equilibrium constant to the pressure. And because we use this equation here, we see, because of the mismatch in the number of moles, we see that pressure is going to have an effect. And in fact, pressure is going to have a half power effect because there is 1.5 moles on the right-hand side versus 1 mole in the left-hand side. And so that is now the equation. If we know what the temperature is, we can then determine the value of K. And so at 2500 Kelvin, we find that the log of K is this, and therefore we can say that K is equal to this value here. We put that in as the left-hand side, and then we can solve as a function of pressure the value of Z. And so if our pressure is 1 atmosphere, this goes away because the reference pressure is 1 atmosphere, and we can solve for Z, and we find that Z is equal to 0.129. If we cause the pressure to go up by a factor of 10, we now have the same temperature-dependent value here, but we also have then now pressure to the half, which is 3 point something, and now we solve that and we see that the value of Z, instead of coming out to be equal to 0.129, we see that Z is about half of that, 0.062. And so what that tells us is, in this particular problem, at the temperature in question, the temperature of 25 K, what we see is that whenever the pressure is 1 atmosphere, we have a higher value of Z here, or CO is being formed, but whenever our pressure goes up to 10 atmosphere, we see that only about a half of the CO is being formed. And so this is then, because we have added an additional species to the products, we had to then involve the equilibrium reaction. And this is one way, a very simple problem where we are able to actually do the math to solve for the value of z. And so what we'll do next is we'll actually look at the test software, and we'll do this same problem using this test software, but then we'll expand it we'll allow more and more species to possibly be there as we allow the test software to do, again, the math. And again, what the equilibrium constant did for us is it looked at this product, and at the temperature and pressure, it determined that the Gibbs function for the mixture was at a minimum whenever the z was calculated to be what we said it needs to be. And so it's driving the mixture to a minimum in the Gibbs free energy. And that is the equilibrium composition that would then exist at that temperature and pressure. Okay.